This is chapter 0, Introduction and Motivation of this course. And we're going to recall what I like to call the virtues of both computer science and mathematics, and check in what sense they also apply to numerics, which is in many ways on the intersection between computer science and mathematics, as you know. But on closer inspection, it seems that numerics is more like an engineering discipline, not something between and shared by computer science and mathematics. And the purpose of my research and of this course is to get numerics back into the realm of computer science and mathematics, back from engineering. And as a first step, we're going to recall similarities between computer science and numerics with respect to data abstraction. And then we're going to recall this data abstraction from the perspective of hardware data types and compare these hardware data types to mathematical data types, which in the sense of model theory amount to mathematical structures. And it will turn out that there's going to be a discrepancy. And we're also going to recall the difference between programming and software engineering, which is a subtle difference that is generally blurred in engineering approach to computing, but we're here in the computer science department, and therefore I'd like to recall this subtle difference. And then we're going to look at classical or standard numerics that has been pursued for the past 35 years as spurred by the IEEE 754 standard, which formalizes floating point numbers and floating point computation, and which has enabled hardware support of floating point numbers. And but we're also going to recall some of its deficiencies, in particular with respect to the consequences it has on the reliability in numerics. And we're going to recall that with several examples, including some examples from your zeroth assignment. And then we're going to recall some numerical problems from the rigorous perspective of computability as introduced by Alan Turing. And we will debunk some numerical myths and confirm some other, and thus put classical numerics on a sound computer scientific foundation. Okay, so let's start by recalling the virtues of both computer science and mathematics. And among these virtues, so on the bottom line, you see the classical virtues from Christian and from Greek methodology. And here's Ada Lovelace, another virtue, the first programmer in many ways. And the 5 virtues of computer science are: first, specify the problem before start to approaches to find an algorithmic solution. And this is also shared by mathematics, where a problem is first formalized before starting to solve it. For instance, solving the millennium problems about Navier-Stokes equation, one of them, it's precisely specified what is the problem in the millennium problems. Then using formal semantics, that means basically which methods are permitted to solve the problem, what is considered, what will be accepted as a solution to the problem. So that basically means in our setting of computer science, which operations can we use to solve the problem. Having more operations can make a problem much easier to solve, but also more unrealistic, as you may or may not recall from my lecture on algorithms. Then start solving the problem in the sense of designing algorithms that use the operations and their semantics in order to solve the rigorously specified problem. So this third step already relies and builds on the previous two ones, and then analyze the algorithm, both with respect to its correctness, does it really solve the problem, and the cost of the algorithm, how much usually time does the algorithm take asymptotically as a certain parameter n grows, and what amount of memory, and there are many other ways of measuring algorithmic cost. So correctness and efficiency. And finally, the fifth and last, some say the top art of computer science is proof of optimality of an algorithm. That's really the core of complexity theory. And now let's recall these 5 virtues, whether in what sense they are also applied to numerics. And it turns out that numerics is more interested, it's more an engineering discipline, it's more interested in actually solving practical instances without really specifying what it means to be practical. And that's not at all a criticism of the achievements of numerics and engineering in general, but it's just that this is not the way that science, and in particular computer science and mathematics, should and would approach such questions. And the goal of this lecture, the goal of my research, is to put back the rigor, scientific rigor, into numerics, and to motivate and illustrate why, for instance, hardware-supported floating point numbers according to IEEE standard have some deficiencies, and maybe serious ones. Let's recall historically the example of the computer game of Civilization. In this game, the player is ruling some country of choice, and the neighboring countries are ruled and governed by the computer in some first form of artificial intelligence. So the rulers, for instance, of India was Mahatma Gandhi is being simulated by the computer player, and each ruler's behavior is described by some parameters, and Gandhi's parameter for aggression is a very low one. It's 1, to reflect that Gandhi was a very peaceful person and leader. And another rule of in this computer game is that when during the course of a evolution and the game progress, when a country adopts democracy, then its aggression level decreases by 2. So that seems like a very reasonable rule for very ancient artificial intelligence. But what happens when India develops democracy? Then Gandhi's aggression level decreases from 1 by 2, resulting mathematically in an aggression of -1, so even less aggression. But since this game from the 80s was run on a computer where the parameters were implemented as bytes, decreasing the byte 1 by 2 would result in a wraparound and would actually result in the aggression level being 255, the highest possible level, very aggressive behavior, and in consequence, in most runs of the game, Gandhi would eventually start a war with his neighbor countries, which is kind of paradoxical, or kind of a joke of the game, a running gag of the game, but basically it's a programming error. And if you think about it, the cause of this program error was a discrepancy between the mathematical data type of integer, where 1 minus 2 equals -1, mathematical data type on the one hand, and the computer scientific data type of byte that's supported and provided by hardware, where 1 minus 2 is equal to 255, not -1. So 2 data types, and they disagree, that's the cause of this programming bug. And please keep this in mind when we similarly look at the mathematical and computer science data types for real numbers. So actually, data types, data structures share many similarities both in computer science and mathematics. Maybe the common topic is abstraction. Ignore and hide details of the data type and instead only refer to and focus on the properties. And to illustrate that, recall that your computers composed from transistors, and several transistors combined give rise to an integrated circuit like one or many logic gates, and these many integrated circuits together give rise to the computer hardware. On top of the hardware, there's a basic input-output operating system, and on top of the operating system, there are software libraries. On top of the libraries, there's some maybe interpreter that interprets your Python code or your Java code, and Python and Java code in turn constitute high-level programming languages. And the benefit of abstraction is that when you write a program in Java or in Python, you don't need to, and you're not even supposed to be aware of all these lower layers, right? That's exactly the essence of abstraction. You don't need to know about the material science of semiconductor transistors. You don't need to know about how integrated circuits operate and what integrated circuits. Not even need to know about the computer hardware or maybe even the operating system. That was the reason Java was introduced, to be able to write user programs that run on all kinds of operating systems and so on. And further advantages that it is now possible and easy and recommended to replace part of these layers transparently to the user. For instance, an interpreter can be replaced by a compiler in order to get increased performance, for instance. And the high-level programming language user program will not know this. For instance, this is how Java just-in-time compilation works. Okay, so hiding details, that's the basis of modern computer science. Replacing one operating system by another is another example, or replacing entire blocks of this hierarchy transparently. And similarly, algorithm development also proceeds in layers, maybe top bottom rather than bottom up. For instance, a popular algorithm for approximating the metric traveling salesperson problem. There are many such algorithms for solving this problem, and one such algorithm is Christophidis' algorithm, as you may have learned in algorithms classes. But Christophidis' algorithm basically consists of two phases. First, compute a minimum spanning tree, and then traverse the minimum spanning tree in a certain way. And so Christophidis' algorithm builds on some solution of the minimum spanning tree problem, and it doesn't really matter which algorithm is used to solve this subproblem. So again, we have an abstraction. It doesn't matter how the minimum spanning tree subproblem is solved, and there are many ways, and one of these algorithms is, for instance, Prim's algorithm. Now, Prim's algorithm, if you recall in turn how Prim's algorithm proceeds, it uses a priority queue. And again, it doesn't really matter much how the priority queue, as another abstract data type, how that is implemented. That's the essence of abstract data types. And one way to implement a priority queue is, for instance, by using Fibonacci heaps, something that we've learned about in CS500 advanced algorithms. Fibonacci heap is a heap It's a linked data structure, so it uses linked data structure as a subproblem, and also it uses totally ordered keys. If you remember the details of Fibonacci heap, if you don't worry, that's not the main purpose of this lecture. Here we're just to recall how advanced algorithms build on several layers, and of course each next higher layer must depend on the lower layers to be fully correct, right? That is true for the hardware, right? So if you imagine a contemporary computer consists of like billions, literally billions of transistors, and among these transistors, millions switch every single second, right? It's running a gigahertz machine, and all of these switches, switch operations must operate reliably. If some of them go wrong, then the entire computation can go wrong. So that's an incredible amount of reliability that is also necessary. Each higher layer must be able to depend and rely on the lower ones fully, not approximately, not usually, not in practice, not most of the time, but always. And that's also true for this layer of uh, these layers of Christophidis algorithm. If some error occurs, for instance, a linked data structure, then entire Christophidis algorithm is worth garbage, right? All our efforts to analyze its approximation ratio are void. So reliability of lower layers, that's the essence of modern computer science. And that actually also applies to mathematics if you think about it. So there's an old saying of Kronecker that God has made natural numbers, everything else has been constructed by the mathematicians. And indeed, if you remember from maybe introductory courses in mathematics, how built on the natural numbers, the integers have been constructed, right? Integers are basically pairs, tuples of natural numbers with respect to some equivalence, some congruence relation. Rational numbers are built on top of integers. Algebraic numbers are built on top of rational numbers, more precisely polynomial rings with respect to some congruence relation introduced by a primitive polynomial, and so on. An entire hierarchy of mathematical data types, structures in the sense of model theory, real numbers, complex number, projective space, Grassmannian, and classes, families of continuous function, of smooth function, of integrable functions, all built on essentially on natural numbers, and logic has in turn built natural numbers on set theory. So that was the goal of mathematical foundations, logic as the foundations of mathematics. And when you prove something in calculus about real numbers, again, you're not supposed, you're not required to recall how real numbers have been constructed. Just the important thing is they can be constructed, built on top of, let's say, natural numbers. And the proofs only involve the properties of the real numbers, not the actual construction. Actually, there are many possible constructions of real numbers, like Dedekind cuts or equivalence classes of Cauchy sequences of rational numbers, but they all give rise to the same properties, and that's what matters. Similarly, for abstract data types, what really matters is their properties and not how they are implemented. So we both have abstraction in both fields, in computer science and mathematics. But now let's look at the differences. And the differences that, for instance, natural or integers in mathematics are or have been implemented using bytes. That was the approach on the previous slide of the computer games Civilization. But the bug, the programming error in Civilization, arose from the discrepancy that the computer scientific data type would disagree from the mathematical data type of integers. So that's a source of program errors, such a discrepancy. And similarly, real numbers are commonly represented in computers by double precision floating point numbers, IEEE for instance, but they are not equal. They differ from the mathematical data type of real numbers. And again, this gives rise to errors, to program errors. And an important part of our research and of this lecture is whether it is and how it is possible to remove this disagreement and replace it with agreement between the mathematical data types and the computer data types. Right. And to this end, let us recall some mathematical and some hardware data types. Namely, for mathematical data type of integers, agreement can be achieved and has been achieved using libraries. For instance, in Java, there's the big integer or the big num, and in Python, integers fully agree with the mathematical data types. And how has this been achieved? This has been achieved by kind of simulating mathematical data type with several bytes. So replacing a single byte with a sequence of bytes of finite but unbounded length. The larger the mathematical integer gets, the more bytes are employed in order to maintain this agreement. But this process of extending the sequence of bytes for this way of realizing mathematical integers and operating on this sequence of bytes rather than just a single byte, and the increasing runtime is happening transparently to the user program, so that the user program doesn't need to worry anymore about possible wraparound effects. So if somebody nowadays were to program civilization, there would not be a cause of program errors anymore, because the data types are in full agreement. And of course, there's indeed a penalty to pay, namely it's a little bit slower. Well, a little bit depends on how many bytes are currently used and how large the integer is that is being operated on. But this is generally preferred with nowadays computers roughly 1,000 times faster than at the time when civilization game was developed. When it prefers to have reliable and convenience and full coincidence between mathematical and computer scientific data types, and is happy to pay the price of some penalty in performance. And if your favorite programming language does not support these advanced data types, then you can still use an external library such as GMP library with C++, so that also C++ supports these mathematical data types in full agreement. And of course, the question how to implement these mathematical data types on top of the hardware data types, that's important, but that's a separate question. And once the goal has been set and achieved to get this full agreement, then the question of efficiency, only then the question of efficiency arises. And one can, for instance, use long multiplication among many bytes to implement unbounded long integers, or advanced algorithms, Karatsuba, Toombs algorithm, Cook's algorithm, Strassen-Schönhage, Fourier-based methods. But all these algorithms, the importance comes after and by realizing that we want full agreement between mathematical integers and computer scientific data types. Good. So how does that work about real numbers? I already mentioned that common ways to use, for instance, floating point, IEEE double precision, or some people use rational numbers, that is fractions of integers, mathematical integers, big integer, big num. But this has disadvantages. There's a reason that mathematicians chose to proceed from rational numbers to real numbers. Remember, some Greek person was drowned 2000 years ago for observing that the square root of 2 is not a rational number, and thus forced mathematicians to extend the rational numbers with algebraic and later with real numbers, and there's a reason. Superficially, real numbers seem to be more complicated than rational numbers, but their properties are much more simple and more elegant, because real numbers, for instance, satisfy the intermediate value theorem, which rational numbers don't, and floating point numbers don't either. Real number interval from 0 to 1 is compact and complete. Rational interval from 0 to 1 is not compact and not complete. Real numbers give rise to fixed point theorems like Brouwer or Banach fixed point theorem, but over the rational numbers, these theorems are wrong. There's a logical completeness, according to Alfred Tarski, of the real numbers as axiomatized, but no such completeness holds for rational numbers, as Julia Robinson proved based on the earlier work of Kurt Gödel. And floating point numbers even violate more properties, namely as elementary properties as the associative law and the distributive law. Both are violated by floating point numbers, which requires even more care for programmers when writing code for these. Right? And Peter Collins likes to, he's a colleague of mine at Maastricht University, also working on foundations and practice of real computation. And he likes to ask his students, suppose you meet aliens, like here in the movie Independence Day, would aliens also use floating point numbers? Would aliens also use IEEE standard? Aliens would certainly also know about natural numbers and integers. If you remember, that was the basis of the science fiction movie Contact with Jodie Foster, communication based on prime numbers. So aliens would certainly also know about prime numbers, which is an indication that this is something inherently mathematically and not something artificially introduced by us mathematicians. But for floating point numbers, I'm not so sure whether aliens would arrive at also use floating point numbers. They would maybe introduce real numbers, but not floating point numbers, and definitely not the IEEE floating point numbers that we operate on. And therefore, this is indication that floating point numbers is really something artificial and not something natural and canonical, as opposed to real numbers with their nice properties. And that is reflected in many ways. For instance, the semantics of floating point numbers is highly complicated. If you read the IEEE document that formalizes floating point numbers, this is very long and very complicated to really fully understand. And there are many exceptional cases. For instance, there's a plus and minus infinity. There's a plus and minus 0. They are not the numbers, they are denormalized numbers. So it's highly complicated semantics, whereas the semantics of real numbers, as I mentioned, is very elegant and concise in the axiomatization of Alfred Tarski. This is demonstrated, for instance, by asking about the semantics of comparison for equality. You probably have learned and heard that you're not recommended, you're discouraged from testing for equality. And why are you not? Well, because of the rounding errors. The rounding errors make quantities that coincide mathematically disagree computationally, right? That's the essence of this discrepancy between um, between the mathematical and the computer science data type. Things agree mathematically but disagree computational, and therefore tests for equality are very unreliable. But the question is, what about semantics? What should we use instead of tests for equality? Can we test for inequality? And well, the thing is, if we could test for inequality, then we could recover test for equality as a Boolean combination in this very sense, right? Which is a contradiction. So there's no test, at least no reliable test for inequality either. So there's no reliable test at all. And that's indication or demonstration that the semantics of floating point numbers is a very subtle one, and we would like to replace it by the elegant semantics of real numbers, right? And things become even more involved, if not messy, when we proceed from single numbers to higher types such as functions, not to mention functionals and operators. This is very yeah, I'd like to call it messy. What is the semantics of a function in floating point arithmetic? And this gives rise to many ongoing research like grids, function replacing a function on this complex domain with a function on a grid, and designing such grid. This is all ongoing research demonstrating how well. The research is very valuable actually, but my perspective is that all these details should be hidden under a layer of abstraction so that real functions are actual real functions in the mathematical sense and not functions on such complicated grids, which make things very complicated. So this is a kind of the vision, and let us also recall the difference between writing program, coding, and modern software engineering. In the early days of computer science, it was fully sufficient to write programs by coding, right? But nowadays, programs and software projects have grown to such complicated endeavors that we need the modern methodology of software engineering. So the early days, a computer would have like 64 kilobytes and run at 1 megahertz. And programs were tested for correctness empirically using the hardware data types I mentioned before. And this was very inconvenient and elegant, but since the resources were very limited, I myself was willing to pay all this inconvenience and unelegance to get to squeeze all performance out of the hardware that the hardware would support. Although it frequently gave rise to bugs as in civilization, and performance was measured in absolute time, like in seconds or minutes or hours. And all this has been replaced right in low-level programming language, for instance, in assembly language. And all this has been replaced. Nowadays, this programming, this coding phase, the implementation is just the last step of a long hierarchy of steps in software engineering, beginning with rigorous specification. Recall, this is one of the virtues of computer science. Then algorithm design and analysis, proof of optimality, and then design and build axiomatic abstract data types, a hierarchy, building like, for instance, on top of bytes, building integers like big num, on top of integers build totally ordered keys like where we used in the priority queue, or as labels for minimum spinning tree weighted edge weights. and then maybe even arrays of such types, or files of such types, an entire hierarchy of abstract data types. So that allows to actually subdivide a large programming software project into smaller modules, into smaller data types that can then be developed and relied on independently, and that can be replaced without affecting the correctness of the overall program. And low-level programming languages with a high performance have been replaced by the convenience of high-level object-oriented programming language, which may incur a penalty in performance, but the convenience and reliability and elegance is preferred nowadays. And also this allows for formal verification as opposed to the empirical correctness in the old days. Formal verification, of course, means that we can really rely and we didn't miss any exceptional cases. And then comes the implementation phase. And now let's look at how numerics has been pursued since 1985, when the IEEE standard was introduced. Well, at first this gave a huge boost to numerics. First, having a standard, of course, is a big achievement because it means that for the first time, numerical programs could be transferred from one computer to another, provided that both computers implemented the IEEE standard according to the standard, right? So that allows for interoperability of numerical code. And then second boost that came actually in the same year, 1985, was when floating point numbers were provided by hardware support, giving a huge performance boost, right? From software to hardware, that is easily a factor of 10 faster. So suddenly numerical calculations became very, very fast. But since 1985, there has not been really much of a change. And still nowadays, these floating point numbers are the foundation and are used, for instance, in MATLAB. Okay, and so floating point numbers, as we know, differ from real numbers, giving rise to errors with a similar source as the error in the computer game of civilization. And programming in numerics is taught with such textbooks like Numerical Recipes, nowadays already in the 3rd edition, very successful, very important, very popular, but it's called recipes, right? It's not called algorithms for a reason. And the reason is that there's lacking specification. The very first point of the very first virtue of computer science is violated by these textbooks. They claim, and indeed it's true, that their recipes work well in practice. They do. But what does it mean in practice? What is practice to a mathematician or to a computer scientist? An engineer knows very well what practice is, but in science, we want to be rigorous. We want to write down what is practice and what is not practice. And that's exactly the essence of rigorous specification. And this is reflected also in the popular NAG library, Numerical Algorithms Group Library, where, for instance, the specification, in quotes, of the function nag opt1 var deriv says that this normally computes a sequence of x values which tend in the limit to the minimum of f of x. So intuitively, this is supposed to minimize a user function capital F by finding a minimum, and the specification of this library says it normally computes such a sequence. And as an engineer, of course, I know what it means normally, but as a mathematician and computer science, this is not sufficient. We want rigorous specification. And tend in the limit also raises the question, how fast, how many iterations should we apply to be close to error, let's say 1/2 to the n to the actual minimum. And this is also not provided by this library. It lacks rigorous specification. And actually there are several reasons why it cannot provide that. One of the reasons is because it's based on floating point numbers. And another reason we will see on the next slide is due to Ernst Becker, namely that it is fundamentally impossible in general to compute such a sequence that tends with a computable rate of convergence to a minimum. So that's many, how to say, many deep deficiencies in floating point number computation. So what we actually want and develop is not numerical recipes, but numerical algorithms that comply with all these virtues of computer science and of mathematics. And the lack of such algorithms, the use of recipes, creates bugs the same way that using bytes instead of integers created bugs with the computer game Civilization. For instance, here you see the maiden flight of the Ariane 5 rocket, and it was not successful. It deviated from its course and finally had to be exploded because there was bugs in its numerical code. There were some undetected overflows, some kind of numerical counterpart to the wraparound effect that led to the bug in Civilization. And another example is the failure of the Sleipner A oil platform in Norway, which also was designed using computer-aided design methods, numerical codes, and there were some error in the code that resulted in a flawed design, and the flawed design in turn resulted in the collapse of that platform. So in the end, it was the lack of having reliable numerical algorithms that turned out to be extremely costly, but fortunately not dangerous because no one was hurt in this case. But just imagine other instances like space flight or airplanes or computer surgeons or care bots where the software errors, numerical software errors can lead to disastrous consequences. Computer science has been pretty good in developed methods that detect and avoid software errors in the discrete realm, but not in the continuous realm, because one of the reasons because in the continuous realm, continuous is actually discretized using these floating point numbers. So to quote from a famous numerical scientist from Cornell Institute, who wrote, "Over the years, I've sat on many PhD qualifying examinations or dissertation defenses for engineering students whose work involved a significant amount of numerical computing. In one form or another, I invariably asked, how do you know that your answers are as accurate as you claim?" Right? So in practice, they are, but how do you really know scientifically? After an initial blank or hostile stare, I usually get an answer like, "I tested the method with some simple examples and it worked. I repeated the computation with several values of n and the results agreed to 3 decimal places." Or more lamely, the answers looked like what I had expected. These are approaches and answers common to engineers, and they're actually in practice most of the time that's okay, that works well, right? But this is the essence of and the difference between engineering and science and mathematics. We want more reliable answers. We want to replace recipes with algorithms. And that such discrepancies and reliability can be a real issue is is actually the second of your homework assignment. Namely, you're asked to calculate, to implement and calculate the following recursively defined sequence. So it's a nonlinear recurrence, right? There's division involved. These are two initial values. Now, if you analyze this mathematically, you see that it converges to 6. But if you implement it, you're going to realize that it does not converge to 6. It converges to 100, even if you increase the precision. So here's an example of a MATLAB function, but I want you to really experience this discrepancy, and therefore I've made it a homework assignment. The second homework assignment is refers to the logistic map, which is another recursively defined sequence, namely like this, where a sequence of real numbers between 0 and 1, where r is a parameter, which in this example is going to be, what is it? Yeah, it's part of the homework assignment anyway. So this is a recursively designed sequence between 0 and 1, and your goal is to evaluate this sequence up to error 10% and see how far you get. So here's how far I got, but let's leave it up to you. And let's discuss the homework when you've submitted it. So Numerics has been extremely successful. It has to be said. Many problems have been solved numerically. In engineering, it's a common tool, computer-aided design, and actually it's even a tool in pure mathematics, in so-called computer-assisted proofs. But this success somehow has led to never ask the question whether there's things that cannot be computed, right? When some things seem to be harder to compute and some things seem to be more easier, right? Like degenerate cases generally seem to be harder to compute, but if there's something that fundamentally, ultimately cannot be computed, is there some real counterpart to the halting problem, which in computer science we know is uncomputable? And similarly, is there some counterpart to NP problem that is computable numerically, but it is provably hard to compute? Provably, not just empirically, but provably. And indeed, such problems and such a theory exists, and we're going to learn all about this theory, first from computability, discrete, and then real computability, then complexity, discrete complexity, P versus NP, and then real complexity. And all this theory has been developed or started actually by Alan Turing when he, in the same paper where he developed the Turing machine and proved the halting problem undecidable. But very recent research only has been extended that beyond real numbers and real functions. And this is what we're doing in our lab. And this will be the final chapters of this lecture towards November and December. Okay, so let's report for now here without proof some things that have been formally proven as uncomputable in the real sense. So Ernst Becker, a Swiss logician, proved that there's a computable function in a sense that we'll formalize later in the course of this lecture. Computable function from 0, 1 to 0, 1, which is continuous and therefore it must attain its minimum mathematically, right? Actually, it's even smooth, see infinity, but it attains its minimum in no computable point, right? And no computable here really means it's provably uncomputable. It contains the halting problem encoded in binary in some sense. So it's really fundamentally uncomputable. And in this way, Becker has opened the eye to numerics, to problems that are not just empirically hard to compute, but fundamentally impossible in a rigorous scientific sense. Another example that I'd like to report here that we're going to look at more closely in the course of this lecture is the wave equation here, second order linear partial differential equation with a given initial condition f and first order initial condition 0. So this is the wave equation, and Poel and Richards have constructed a computable initial condition such that the solution provably is not computable in the sense that it contains an encoding of the halting problem, thus answering or providing, demonstrating a blind spot to numerical scientists. There are problems which are fundamentally not computable. Another example, even more interesting from a logical perspective, is a counterpart to the Brouwer's fixed point theorem. Brouwer says that every continuous function from the unit square to the unit square must have a fixed point, right? So that's generalization from one dimension to two dimension. And Orevkov constructed a computable such function which has no computable fixed point. Mathematically, it has, of course, a fixed point. Actually, it has many, but his construction in such a way that none of these fixed points are computable, similar to Specker's construction. Of course, this function attains its minimum in many points, but none of them are computable. What makes Orevkov's construction even more interesting is that his fixed points do not contain an encoding of the halting problem. They cannot. There's a deep theorem of Robert Sorry that says computing these fixed points may be uncomputable, as it is the case for Orevkov, but not complete for the halting problem. Very interesting. But this is, at this stage, we're not even supposed to understand this subtlety. We're going to address this as the course of this lecture. And final, how about the semantics of equality and inequality? As you recall, actually, we're going to give an answer to this question. We're going to show that this is not related to floating point numbers. Test for equality is inherently impossible. It's equivalent in a rigorous sense to the halting problem, to the complement of the halting problem, but it can be made computable when relaxing the semantics to multi-valued semantics, or alternatively to partial semantics. And if you're not don't understand what this means right now, that's exactly the point of this lecture, to explain all this. Okay, so right, so we're approaching the final 15 minutes of today's lecture, and I'd like to end this with a suggestion for a self-check. Right, you may or may not worry whether your background is sufficient to make it through this lecture, and I assure you that the background is not so deep. Actually, you may want to recall your lectures on calculus 1, 2, maybe even calculus 3, but definitely calculus 2 to answer this question. But once you do that, then you're going to be fine with that's all we're going to need throughout this lecture. So you're all computer scientists. Actually, I was hoping that half of the audience would be mathematicians, worrying about their lack of computer scientific background, and I would have convinced them that, again, this is easy to catch up, but for you, you may be mostly concerned with mathematical background. So please recall, look up, that's part of the homework assignment number 0, what it means for a function to be continuous, what it means for a space to be compact, what it means for a sequence to converge, and in particularly look up several common notions. There are several notions that are equivalent in some cases, but not equivalent in other cases, and it's very instructive to recall all these notions and to compare them when they are equivalent and when they are not. Convergent sequence, continuous function, compact subset, metric space, maybe a little bit of logic. If you don't know much about logic, don't worry. The logic that is taught as part of discrete mathematics here at KAIST is completely completely sufficient. On computer science, well, if you've attended CS 300, you're going to be mostly fine. If you even attended CS 422, theory of computation with halting problem and models of computation, that's even better. We'll maybe talk about Oracle machines. If you don't recall that, don't worry, that will be covered and provided by the lecture. P versus NP, you're probably familiar with it because that's how people try to become famous these days. But more important is the notion of a reduction, polynomial type reduction, and we're going to talk about computable continuous reduction, and maybe a little bit of approximation algorithm, but like Christophidis, but in the real setting, this is not fully necessary. We're going to recall that anyway. There will be some implementation assignments. There will be some mathematical assignments where you're asked to prove something. There will be some computer scientific assignments where you're asked to develop a real algorithm. But there are only a few implementation problems, like in current homework number 0. So if you're not comfortable with that, don't worry too much, but it helps to know C++ and Linux. Right, this is already the end of the first lecture of the introduction and motivation. And right, so in the final few minutes, I'm available here for questions and discussion. And otherwise, hope to see you again.